Okay, number 7. Among 2,200 randomly selected male car occupants of age 8, so these are 8-year-old boys, 72% wore seatbelts. Among 2,380 randomly selected female car occupants of age 8, so 8-year-old girls, 84% wore seatbelts based on data from the US Department of Transportation. I don't know if that's real data. I think that I got this question from another stat teacher. I think they just made that up. Those numbers seem really low. So let's use a 5% significance test to test the claim that females are more likely to use seatbelts than males. So for each individual in this study, we have 2 pieces of information. Are they male or female? And did they wear their seatbelt, yes or no? So this is 2 variables, and they're both categorical. It's male or female, seatbelt, yes or no. Neither of those are numbers. So this has to be a 2-sample t-test or a chi-square test. This time, unlike our previous 2 categorical variables up here with the helmets and the crashes, there's only 2 options for each. So it looks like we're splitting into our groups, the male group and the female group, and then we're just saying, like, are you wearing a seatbelt, yes or no? And that's exactly the type of setup that we would use for 2-sample T. Okay, there's some proportion that we're focusing on here. It's the proportion wearing seatbelts, and we're comparing that proportion in one group versus the proportion in another group. So that's the perfect setup for 2-sample T. And we want to do a 5% or a hypothesis test, and 5% is going to be our significance level. Now, this has happened a couple times already, but I am going to use not equals as my alternative hypothesis. The question is hinting that we would use females greater than males. So like whichever group the female group is should be the bigger one in the alternative hypothesis. So that would be fine too if you ran the test that way, but I'm going to stick with the default of just not equals. That's just sort of the safe standard thing to do. And we need to sort out this 72% and this 84% because Minitab wants a number. Like out of 200 or 2,200, they want to know the number of boys that wore seatbelts, not the percentage. So what's 72% of 2,200? So 0.72 times 2,200 is equal to 1584. So this is equal to 1584. And 84% of 2,000, so 2380, what's 84% of that? That is 1999. Okay, so actually it's 1999.2, but presumably it was like 1999 individuals, and then they rounded the percent off when they gave us this information. So the first group is going to have 1584 out of 2,200. The second group is going to have 1999 out of 2,380. So let's flip over to Minitab and get those numbers into a 2 proportion setup. So we're looking at 2 proportions. We have summarized data. First group, it was 1584 out of 2,200. And the second group, it was 1999 out of 2,380. Okay, and hypothesized difference is 0. Our null hypothesis for these 2 groups is always that the groups are the same, and I'm going with not equals. Again, the question hinted that we should make the girl side bigger, so that's a less thing because I made the boys group 1, so group 1 is smaller than group 2, but I'm going to stick with not equals here. So let's just see what we get. Our p-value is what we're looking for. It is very, very small. Let's get a bunch of extra decimal places. And actually, so how many decimal places did I do? I did 14. So out to 16 different decimal places, it's still 0. So I don't think that's happened before. Usually we start getting some numbers. So wherever the numbers start, it's beyond the 16th decimal place here. So of course, this is very strong evidence that there is a difference between the 2 groups. Okay, so not only are they 12% apart, but the sample sizes are in the thousands. So a big gap and a huge sample. So very, like, it's the strongest evidence we've seen yet. It's 9 standard deviations down the side of the bell. All right, next question. A study of the effects of prenatal cocaine used on infants. A random sample of 35 infants conducted, their birth weights was measured. Okay, so based on the sample data, the mean was 2,700 grams with a standard deviation of 645 grams. Let's find a 95% confidence interval. Okay, so for each of these kids, we have one piece of information, which is how much they weighed. That's all we have. There's no other piece of information we have about these babies. So we have one variable and it's quantitative. So this is a one sample T question and it's asking for a confidence interval. So we'll flip back over to Minitab. Stat, basic statistics, one sample T. This time we have summarized data. There was 35 individuals in the study. Their mean was 2,700 and their standard deviation was 645. We are looking for a 95% confidence interval. So 95%, and we're not bothering with a hypothesis test this time, so I'm just gonna uncheck that. Okay, so there's our confidence interval, 2,478 up to 2,922. Okay, so what did the cocaine have to do with this? Like absolutely nothing. We just have weights for a bunch of babies and we want to find a confidence interval for the mean weight of all the babies that this sample represents. Okay, so that's it for that question. Just needed to get to one sample T and plug the numbers in. Question number 9. A study conducted in the University of Melbourne indicates there may be a difference between pain thresholds of blondes and brunettes. Men and women of various ages were divided into 4 groups according to their hair color: light blonde, dark blonde, light brunette, dark brunette. And then they get some kind of pain threshold score. So we've separated into 4 groups. That's one variable, what your hair color is. And then we measure a second variable, which is this pain threshold score. So we had another situation where we were comparing 2 groups and then measured a number. That was this service and not service. We used 2 sample T there because there was only 2 groups. Here we have 4 groups. We have to use ANOVA, which is our test for comparing more than 2 groups, and we have a number for each of them. So I'm copying and pasting the data over here. Here's the table, and I put the headings at the top. So let's run ANOVA. So the usual one-way ANOVA on these 4 groups. So response are in separate columns. So let's get all of those columns in there. And histograms, interval plot. Yeah, we'll get this graph. Okay, so assume equal variances. I've always unchecked that, haven't I? So I'm going to uncheck the assume equal variances. I think I've unchecked that in the past. And let's see what we get. So the dark brunettes have the lowest numbers, the light blondes have the highest numbers, and the light blondes almost don't overlap with the dark brunettes. So do we get a p-value that's significant? Kind of 0.019. That's pretty small. If we're testing at the 5% level, then that's small enough. Okay, so yeah, so the question said, state the hypothesis. Well, the null hypothesis is that all the groups are the same. The alternative hypothesis is that they're not all the same. And the test statistic, I didn't talk a lot about that, but that's usually like the numbers in this table are basically like the various numbers that go into computing the p-value. That's what it means by test statistic. Some of this language is left over from other people who contributed to this review sheet. So test statistic is not something I would ask for on the exam, but I would ask you for the p-value. And so that's 0.019, and I might ask you for your conclusion. So here, this is less than 5%, so we do have strong evidence that there is a statistically significant difference between the groups. And it looks like, from the picture, the main difference is that the light blondes have higher numbers than the dark brunettes, and the others are in the middle. They're not so different. They might be the same as some of the other groups, but we could say that the one group on the light end has higher numbers than the one group on the dark end, and the middles are sort of like, we don't really know where they fall. Okay, so that's it for this video, and then we'll do the last 3 questions in a last video.